video, we are presenting a traffic predictor governed by ML techniques. As the name suggests, it is creating and training models to predict traffic, which is the number of vehicles. Why predict traffic? Traffic congestion is rising in cities around the world, driven by factors such as growing urban population, aging infrastructure, poorly synchronized traffic signals, and lack of real-time data. These impacts are significant. One key approach is traffic prediction. Traffic prediction means understanding traffic flow to detect traffic conditions for upcoming periods such as next day, week, etc. For this project, we started with analyzing the data from the dataset, then pre-processing it, cleaning the data to make it feasible for our project, then implementing models such as linear regression and KNN, then decision tree and gradient boosting, finally random forest and tuning the hyperparameters.
Our model leverages a dataset which has 4 key features: datetime, junction, vehicles, and ID. Here, datetime is the precise timestamp for when the measurement is recorded. Junction is a location identifier for the specific traffic junction. Vehicles denote the actual number of vehicles, and ID is the unique identifier of a sample. Our dataset is recorded on an hourly basis. This data spans a period of nearly 2 years, capturing from November 2015 to July 2017. This graph also shows us that we have 4 junctions.
As we saw, there were 4 features in the dataset: date time, junction, vehicles, and ID. After pre-processing, the features that extracted and retained are junction, year, day of month, hour, month, weekday, and the target variable is the number of vehicles. Each of the features, categorical or not, have been described as integers. The significant features that retain after pre-processing are year, month, day of week, and hour. And as mentioned before, the target variable is the number of vehicles.
The proposed approaches for prediction are as follows: linear regression, decision tree, KNN, gradient boosting, and random forest. We employed calculating R-squared scores for calculating how well the regression model explains the variability of the data points around the mean. A value of 1, which is 100%, indicates that the regression model perfectly fits the data. If it is 0, it indicates that the regression model does not explain any of the variance in the dependent or target variable. A percentage of 59.3% for linear regression indicates that the model does not perfectly fit the data because our data set does not have a linear relationship, whereas a percentage of 94.8% indicates that the model nearly perfectly fits the data.
Now 3 more methods. The R2 scores for these corresponding methods are calculated using the best hyperparameters using the hyperparameter tuning. The highest value of random forest's R2 score denotes that ensemble methods are best for the regression tasks.
Here is a comparison of R-squared scores of various models that we implemented on our dataset. As we can see, for linear regression, the R-squared score is least, which means that the linear regression model does not fit well to the dataset. The value of R-squared scores are best for random forest and gradient boosting methods. Hence, we conclude that these ensemble methods outperform linear regression by effectively capturing complex data dependencies, thus providing more accurate traffic predictions. Now we'll see a demo of our predictions.
This is a user-friendly interface that allows us to effortlessly predict traffic volumes. We can simply input all of these parameters. For example, 1, 2015, 11, day of month 1, hour to be 0, and weekday to be 7. This predicts our number of vehicles to be 15. Thank you.